Okay, so now what we're going to do is use the pairwise Cosine similarity matrix as input to the adjacency matrix based eigenvalue program to determine the principal eigenvalue of the pairwise Cosine similarity matrix. And we can formulate the network-wide similarity index measure as the ratio of this principal eigenvalue of the pairwise Cosine similarity matrix and the number of nodes in the network. And the closer is this ratio to 1, the more similar are going to be the nodes with respect to the features we have considered. Again, remember that we discard nodes that have all zeros in their feature vector. So the pairwise similarity score that we measure based on the remaining vertices may not be a true reflection of all the vertices because we are discarding nodes that have all zeros in their feature metric vector. Okay. But if no vertices are discarded, then it's a reasonably good measure of a network-wide similarity. Okay. So this is the pairwise Cosine similarity matrix that we got from for this graph in the previous. This is for this, yeah, for the graph and this weight, height, and age data. We got this pairwise Cosine similarity matrix in a previous video. So you can save this as a matrix and feed into our adjacency matrix based eigenvalue program, and you're going to get these eigenvalues. The largest among these eigenvalues is 5.88689. Divide that by the number of vertices, and what do we get is going to be the network level similarity index. So the principal eigenvalue is always going to be less than or equal to the number of vertices. So that's the idea here. Now, if all the entries other than the diagonal, if diagonal is always going to be zeros, but if all the entries are 1, that means the two corresponding vertices are exactly similar to each other. So if the vertices are exactly similar to each other, then all the entries are other than the diagonal are going to be 1, then the principal eigenvalue of such a matrix is going to be the number of vertices, which is in this case 7. So that's why we are dividing this by the number of, that's why actually we are using the pairwise Cosine similarity matrix as the basis to compute this eigenvalue and divide that by the number of vertices, because if all the entries other than the diagonal, of course, are 1, that means that's the maximum level of similarity can have between any two vertices, and the principal eigenvalue for such a matrix is going to be equal to the number of vertices. So that's why we're dividing the principal eigenvalue of the pairwise Cosine similarity matrix by the number of vertices. So the maximum, it could be 1, and that's a measure of the maximum similarity between among all the nodes in the network. Okay, so I'm going to show now how to do this. So you can start with the raw data, and get the pairwise Cosine similarity matrix. Okay, so this is a pairwise Cosine similarity matrix. I can save this to a file. So make sure you can save it as a .text file. Okay, so I'm going to close this, run the adjacency matrix program, adjacency matrix eigen vector centrality program. So load the pairwise similarity matrix that we just generated. And these are the eigenvalues. Of course, we're going to also get the corresponding eigenvectors. So the largest eigenvalue is what we're interested here, which is 5.8, 8, 6, 8, 9, and so on. So we can use that and divide by the number of vertices. That's going to be the network level similarity index. Now, what I'm doing is I'm going to change just one number here, which is for vertex phi. Instead of age 50, I'm going to make the age as phi. Actually, I made two changes. For vertex 1, instead of age 23, I'm going to make age 3. So I'm going to introduce more dissimilarity. That means I'm going to reduce the similarity among the vertices by changing the values for 1 and 5. I'm going to see whether the network level similarity index reduces. So if you do that and generate the pairwise Cosine similarity matrix, this is what I get. And if you compute the eigenvalues for this pairwise Cosine similarity matrix, I'm going to get 5.4292 as the principal eigenvalue. Divide by the number of vertices, you're going to get 0.7756, which is less than 0.8409. So as you increase the dissimilarity, that means as you decrease the similarity, then the network level similarity index also reduces. Now we can compute this also for our centrality matrix data set. Again, the centrality matrix we are going to discard, remember, nodes 0, 6 and 7 for this graph. But nevertheless, if you use that pairwise Cosine similarity matrix that we got in the previous video for these 5 vertices as input to the adjacency matrix based eigenvector centrality program, you are going to get 3.7397 as the principal eigenvalue, and divide that by the number of vertices you have considered. That is something you have to remember. You should not divide by the total number of vertices. You should divide only by the number of vertices you have considered for the pairwise Cosine similarity matrix. So in this case it is phi. So 0.7479 is the network level similarity index for this graph. Okay, so with this we can stop this video.